In this set of notes, we're going to continue looking at multiple regression. So similar to when we looked at simple linear regression, in order to find the parameter estimates, we use the method of least squares, and we're going to do the exact same thing here. And it ends up that the method is very similar. The idea is that we want to minimize the SSE. The only real difference is that to compute the estimates, the formulas can be a bit more tricky. So we're going to use statistical software to obtain the estimates. Now, one should note, though, that previously the matrix representation of the models that we looked at, we can actually use the matrix representation of the models to get the parameter estimates just like we did with simple linear regression, and then we don't have to worry about the complicated formulas. So this is actually one of the benefits to using the matrix representation, is it can make getting those estimates much easier. So in order to motivate what we're going to look at in this notes, recall that we had this previous example. So in this example, we were looking at level of racial animus across different areas in America by measuring the percent of Google search queries that include racially charged language. And the idea was we built this multiple regression model where we had 4 different predictors and we were trying to predict the animus measurement. Alright, so here what we have is the SAS output where we actually fit the model and got the parameter estimates. So one thing to be very careful here, remember in the previous note set we had that example where I said, okay, hypothetically let's assume that these are the parameters. Here in this note set, we're actually using the data to get parameter estimates. So these are 2 different things that we're looking at here. So do make sure that you're very clear on that distinction. So you'll notice that the SAS output looks very similar to when we looked at simple linear regression. And down here you'll notice that we have the parameter estimates. Now previously when we looked at simple linear regression, we would have an estimate for the intercept and an intercept for the slope. Well, notice here we still have that estimate for the intercept, but now we also have an estimate for the coefficient for each of our 4 predictor variables that we are interested in. So let's look at how to read this output and pull some information from it. So the first thing we're going to identify is the least squares prediction equation. So the one thing to be very careful here is note that this is not the model. When we say least squares prediction equation, this is where we're using our parameter estimates. So remember, whenever we write our least squares prediction equation, this is where we use the y-hat. Because again, we're acknowledging that we're estimating our parameters using our sample data. Now to get those estimates, we're going to go back up to our output. And so notice here again, we've got our intercept. So that's going to be our estimate for beta naught. And then we're going to have our estimate for beta 1. Beta 2, beta 3, and beta 4. So looking down here, again we see that the intercept is 124.319. And then next, our estimate for beta 1 is 0.564. Our estimate for beta 2 is negative 0.578. For beta 3, we have negative 2.054. And then finally, for beta 4, we have 1.519. So again, notice this is not the model, this is the prediction equation. This is where we've included our estimates for our parameters. Alright, so just like before we interpreted the parameters, now we're going to interpret the estimates. So the first one we're going to interpret is the estimate for beta 1. And so I'll write down that interpretation and then we'll talk about it. So we have here, we estimate that the mean animus measurement, so remember anytime we're talking about our prediction equation, we're talking about in terms of the mean of the response variable. So we estimate that the mean animus measurement of a media market will increase by 0.56 for each additional 1% increase in the percentage of African Americans living in the market with all other predictors held fixed. And so you notice this is very similar to the interpretation that we had for the corresponding parameter. So take a moment, pause the video, and see if you can find the value in the interpretation of beta hat 2. Right, so you should have identified that beta hat 2 is equal to negative 0.578, and again that could have either come from our prediction equation here, or you could have went back to the SAS output and found it here. Now in terms of the interpretation, the only thing that's really going to change is you're going to have decrease instead of increase. The value is going to change to 0.578 or 0.58, and then x1 looked at the percentage of African Americans, whereas when we talk about x2, that was looking at the percentage of Hispanics, so we would have changed that there. And then finally, for the value in the interpretation of beta hat naught, that is the intercept term. So if you remember our intercept term in the simple linear regression model, what it did was it looked at when x was equal to 0. Well, we're doing the exact same thing here. So the interpretation of the intercept, here's the value, will be that we estimate mean animus measurement of a media market to be equal to 124.319 when the value of all 4 predictor variables is equal to 0. And so again, it's very similar to the interpretation that we saw when we looked at the simple linear regression model. Next, we're going to look at the estimation of the variance of epsilon. And so, Word has changed this on me. That should be an epsilon, not a capital E there. So the variance of the error term plays an important role in model utility. Again, the larger the value of sigma squared, the greater will be the error in estimating the model parameters. And so, just like we did before, what we're going to use to help us estimate sigma is we're going to look at the MSE. And so remember before, S squared is called the mean squared error, or the MSE, so we could look at the square root of the MSE to find S. And so looking at the interpretation of S, where S is the estimated standard deviation of epsilon, it says we expect most, or approximately 95% of the observed y values to lie within 2 standard deviations of their respective least squared prediction values y hat. And again, this is by the empirical rule. And the reason that we can invoke the empirical rule here is because we have that normality assumption on our errors. If we did not have that normality assumption, then we could not apply the empirical rule here. So if we go back to our SAS output, notice here that the root MSE is equal to 24.78. So what that tells us is our estimate of the standard deviation is equal to 24.78. And so from here we can write out what that interpretation is, and it's as follows. And so one thing to notice that's important here, in this interpretation we do reference our regression model with the 4 predictors. The reason for this is S will change for different models. So if we had only used 3 of those predictors or 2 of those predictors, or if we had added on an additional one, S would change. So it's very important in that interpretation that you do reference the model that you fit, because that value will change for different models. All right, next we're going to turn to testing the utility of the model. And to do this, we're actually going to use an analysis of variance, or an F-test. So if one of our main objectives is to conduct a model utility test, that is to determine if the model is useful for predicting y, we could conduct individual t-tests for each of the beta parameters. So if you'll remember, when we looked at the simple linear regression model, we only had one x, so we had beta 1, and so we could use a t-test to determine whether or not that was significant. However, using those individual t-tests is generally not a good way to determine if the overall model is contributing to the prediction of y. So recall that for the simple linear regression model, the model utility test was based on this fact right here, again when we were looking at when beta 1 was equal to 0 and we only had that single predictor. But now we're going to perform a global test that contains all of the parameters with the exception of the parameter for the intercept. And so here's what our new null hypothesis will look like. And notice in the alternative, we're looking to say that at least one of them is non-zero. So here is our test statistic. It is an F-test statistic. And you can read these notes here a little bit more about that test statistic. Now this box here summarizes the F-test that we're going to conduct. So notice here we've got our null and our alternative hypothesis. We also have that test statistic, and then as usual our p-value and our conclusion. All of these, or the pieces here that you need, are going to be given in the SAS output. And one of the ways that this information is summarized is by using an Anova table. And so the SAS output, and we can get the R output to give us this as well, is actually going to provide an Anova table that corresponds with this particular test. And so here I have the Anova table summarized, and we're going to go back up to the SAS output, and we're going to find the different pieces of this Anova table in that output. All right, so going up here, you'll notice that SAS says analysis of variance. So this whole table right here, this is our Anova table that we're going to use. All right, so I'm going to go back down here and I'm going to fill in what those values are based on the part of that output that I just boxed in. So here are those values. And so the Anova table, the real purpose of it is it really helps us calculate or get to this piece right here. So when we're looking at SAS or R output, really what we're looking for is that F statistic and the p-value. But the rest of the Anova table, if you've seen these before, is really helping us derive that F statistic. And what it does is it partitions out different pieces of variability that we need to consider. So let's look at how we can actually test whether that multiple regression model is useful with alpha equal to 0.05. All right, so just to remind ourselves, this is the model that we are currently looking at. And notice here I am writing the model. I'm not writing the prediction equation. Now, as with any hypothesis test, we always want to make sure that we are aware of what the assumptions are. So if you'll remember, even though we're not checking them currently, we are assuming that our error terms are IID, normal, 0, sigma squared. And again, we'll spend a couple weeks later on actually looking at how to test these assumptions. All right, so we're going to write out what our hypotheses are. So for the model utility test, when we're looking at multiple regression, what we're doing under the null is we are assuming that all of our parameters, with the exception of the y-intercept, or I should just say the intercept, are equal to 0. And then under the alternative, we're trying to prove that at least one of these is non-zero. Right? So if we go back up to our SAS output, or we could look up above at our Anova table, we see that our test statistic F is equal to 26.58. Now, typically in publications, whenever you report an F statistic, it is good practice to also report the numerator and denominator degrees of freedom along with that test statistic. This is another place the Anova table can help us. Our numerator and denominator degrees of freedom are listed here. So the first degree of freedom that's listed is the numerator, so in this case it's 4, and then the denominator degrees of freedom are 191 for this example. And then we want to report our p-value. So in this case our p-value is less than 0.0001. And with a p-value of that size with alpha equal to 0.05, we are going to reject the null. And then one thing to keep in mind is there is a movement in publications now, instead of saying that the results are significant at the 0.05, to just directly report the p-value. So in this case we would say the p-value is less than 0.0001. So in terms of our conclusion, sticking with a more classic conclusion, we would say the following. So looking at our conclusion, one thing to notice here is when we reject the null hypothesis for this particular hypothesis test, we are only able to conclude that at least one of the beta i's is non-zero. We don't know which one is non-zero, and further we don't know how many are non-zero. We just know that at least one of them is non-zero, and what this tells us is that the overall model is useful at predicting animus of media markets. And remember, when we talk about predicting, what we're really talking about here is a prediction on average. Alright, and then just as a caution, a rejection of the null hypothesis in the global F test leads to the conclusion that the model is statistically useful. However, it does not mean that it is the best model. And so that's very important. We could have multiple models that have significant model utility test, and so we need to keep that in mind. Now, once we perform the overall test, that's when we can start looking at making inference about the individual beta parameters. But before performing inference about the individual beta parameters, you do always want to do that global F test as a first step. And so when we look at the individual beta parameters, what you'll find is the hypothesis test is very similar to the hypothesis test for the slope in the simple linear regression model. So I'll have you read this section on your own, and then the test is summarized here. And again, very similar to what we saw in the simple linear regression case. So let's go ahead and determine whether the percentage of those that are at least 65 years old living in the media market is a useful predictor in the regression model at the 5% significance level. So again, you would always want to test your assumptions, but notice if you perform the global F test first, the assumptions are the same. So if you already checked the assumptions for the global F test, then you know the assumptions are met for this test for this particular coefficient. So for this hypothesis test, since we are interested in those that are at least 65 years or older living in the media market, that was our fourth predictor. So here we're interested in beta 4. Under the null we assume that it's equal to 0, and under the alternative we're going to try to prove that it's not. So our test statistic in this case, we're going to go back up to our SAS output. So going back up. You'll notice that here in the parameter estimates, we have both two pieces of information here. Here we have the test statistic and the p-value, and we're going to use this for hypothesis testing. We also have here the confidence interval, which we'll look at momentarily. So going back down, we see that our test statistic in this case is t is equal to 1.7 to 1, and then the corresponding p-value is equal to 0.0891. Now, since this p-value is larger than the significance level we're using for this test, we are going to fail to reject. So notice the overall model was useful, but that doesn't necessarily mean that all of the predictors individually are. So looking at our interpretation or our conclusion, we have the following. So here we say there's not enough evidence to conclude that the percent of those who are at least 65 years old living in the median market is a useful predictor, and then we have to include this last part, which is given that the other three variables are included in the model. It is possible to fit a different model including this predictor where that predictor is significant. So again, whenever we have these interpretations in multiple linear regression, it's very important that we reference back to the model that we fit, because all of our interpretations are going to be contingent on that model. Now the last thing we could do, and I kind of alluded to this already, is we could look at a 95% confidence interval. So again, if we go back up to that SAS output, remember that here was the confidence interval. So for this example, our confidence interval is as follows. And then in terms of our interpretation, we have the following. And it really, in writing this, I don't have to keep that many decimal places. Alright, so we are 95% confident for each additional percentage point in the percentage of those who are at least 65 living in the median market that mean animus measurement will change between decreasing 0.23 points and increasing 3.27 points given the other three variables are in the model. So again, keeping in mind that it's very important that we make sure we reference the model that we're using because, again, the estimates we get will depend on that. The other thing to notice is that this interval does contain 0, and that shouldn't be surprising considering for the corresponding hypothesis test we did fail to reject that hypothesis. And this is going to conclude this note set. There are some recommendations for checking the utility. I would like you to read these on your own.